Okay, let us try to, solve the 6.10 over here. So in the circuit of figure 6.12, RT is equal to 1.8 kilo ohms, RF is equal to 4.7 kilo ohms, RA, RB, and RC equal to 500 kilo ohms. Right, this is R1, sorry. R1 is equal to 1.8, RF is equal to 4.7, RA, RB, RC is equal to 500 kilo ohms. VDC is 10 volts. Supply voltage is plus or minus 15. The transducer is thermistor with the following specification. RT equal to 500 kilo ohms, same as RA, RB, RC at 25 degrees centigrade. The temperature coefficient of resistance is minus 1 kilo ohm per degree centigrade. If the temperature changes from 0 to 75, find the variation in A, that is input signal over there, and the output signal V0. So we should here consider input signal VDC. Okay, this is VAB, sorry, input signal VAB we should bother here, and the output signal V0. Okay, it's rather than calling it as input signal, we should call it as output of the bridge. It should have been output of the bridge. Okay, so the temperature coefficient of resistance is minus 1 kilo ohm per degree centigrade, means as temperature increases, resistance is going to decrease. Okay, so at 25 degrees centigrade it will be 500 kilo ohms. At 0 degrees centigrade it will be, what you call, having a negative temperature coefficient. That means 525 into minus 1 will become minus 25. That minus 25 should be subtracted from 500 kilo ohm. So that means 500 minus 25 kilo ohm will give 525 kilo ohm at 0 degrees centigrade, because temperature coefficient of resistance is negative. And when the temperature increases, say for 70 degrees centigrade, so 70 minus 25 will be 45. 45 into minus 1 will give me the value minus 45. 500 minus 45 will give the value which is 555, 455. So 455 will be the resistance at the 70 degrees centigrade. Okay, at 0 it will be 525. At what you call 70 degrees it will be 500 minus 75 minus 75 minus of 25 value, that will be 500 minus 25 kilo ohms, and that will give us the value which is nothing but 455 kilo ohms. Okay, so this should be subtracted from the value here, 70 minus 500. I'll just tell you the resistance value at different temperature. At 70 degrees centigrade, it will be 500 minus 70 minus 25 into the value 1 kilo ohm per second. Or you can write it something like this: 500 plus 75 minus 25 into minus 1 kilo ohm per degree centigrade. Okay, that will definitely give you the negative value, the reduction value. But for the 0 degrees, it will be 500 plus 0 minus 25 into minus 1 kilo ohm. That will give you 525, what you call, kilo ohms. Okay. So what will be the variation is what he is asking. So for that, so again, we need to just go back to the figure. This is the figure over here. So these are the, RA, RB, RC, and the RT value, which is plus or minus del R. So that means as temperature increases, resistance is going to fall. So plus for falling resistance, minus for, falling rising temperature, minus for the rising temperature, plus for the falling temperature. Okay, so resistance is going to increase if temperature falls, the resistance is going to decrease if temperature increases for this thermistor. Okay. So we will get here the value. So that there is a mistake in this, but I think in the new edition, the mistake is corrected as far as the formula is concerned. So this is the formula with a minus sign. Please remember that this is the formula with a minus sign. VAB is equal to minus del R VDC divided by 2 into 2R plus del R. So generally people might neglect this del R and write only this value, right? But even if you don't want to neglect, it's all right. So you can as well write del R into VDC divided by 2 into 2R plus del R. So the question which he is asking here at the 6.10 is the input signal over there. So what is the input signal? What is VAB? VAB1 at 0 degree, VAB1 at 70 degrees centigrade, both. Then VAB minus VAB, VAB2 minus VAB1 is what you need to find out. And that will give you the value of the variation in the input signal. Okay. So how do you find VAB1? VAB1 will be del R. Del R will be how much? Whatever is the value of del R. So the del R value, rather minus del R value. Minus del R value will be, so the temperature is decreasing. So therefore, here we can just try to write the corresponding value there. So that will be 25, into 10 divided by 2 into 2 multiplied by 500. R is 500 plus again the value 25 over here. So this should be minus 25. Minus 25 into 10 divided by 2 into 2 multiplied by 500 plus 25. Okay. So del R is 25 for 0 degrees. For 70 degrees, this value will be, this value will be what you call 45. This value will be 45. 70 minus 25 will be 45 with a plus sign, and this will be minus 45. This value will be minus 45. This will be plus 45. This will be minus 45. Okay. This will be plus 45 for VAB2. Okay. 70 minus 25 will be 45. That plus 45 divided by minus 45, because the formula is minus over here. It's not plus. Because of the reason that you can see here also VAB into minus of RF by R1. So this minus and the minus which would have been here, that cancels and hence it becomes plus. So here he has written correctly, but here he has written wrongly. So this should be a minus sign. But in the, if you have the hard copy, there it is mentioned as minus. Okay, that minus is missing from this hard copy. Okay, so VAB1 and VAB2, you can find the difference between the two. You will get the value which corresponds to the first case, that is the input signal variation, and then the output signal variation, and that will be straight away, we can use the formula, either you can use this formula. Okay, so that is variation in V0 is equal to variation in VAB multiplied by minus RF by R1, or you can find for each of the VO, VAB1, VO1 is equal to VAB1 multiplied by minus RF by R1. VO2 is equal to VAB multiplied VAB2 minus multiplied by minus RF into R1. Okay, we can use that formula and then find out VO1 and VO2 for each of the VAB1 and VAB2 and find the difference, and that will give us the second part, which is the variation in the output signal V0. Okay, so I'll pause. Okay, so now let us go for 6.11. The transducer in the circuit of figure 6.12 is a CL605 photocell with the following specifications. Minimum dark resistance is 500 kilo ohms and resistance at 0.61 meter candle. So photocell means if light falls, Okay, if light falls, the resistance is going to decrease. Okay, that is what is happening here. Dark resistance is 500 kilo ohms. When something like 0.61 meter candle of lux falls, then that much of light falls on that, then we will have the value of you know uh, resistance to be 7.5 kilo ohms, reduced from 500 to 7.5 kilo ohms. So using the circuit specifications of the problem 6.10, that is for this only, determine the input voltage VAB and the output voltage V0 at dark condition and at 0.61 lux. Okay, at dark condition as well as 0.61 lux. So when dark condition is there, we will have 500 kilo ohm. The RA, RB, RC will also be 500 kilo ohm, right? Photocell is used in place of the thermistor over here. In place of the thermistor over here, we are using the photocell, which is of same thing. So again, if you go back to the figure of the circuit over there, then you can see that it becomes a balanced bridge. If it's a balanced bridge, then naturally the value here will be 0. If the bridge is balanced, then the voltage here will be 0. So that just means that for the first case, that is for dark condition, when the resistor off corresponding to the photocell is 500 kilo ohm, which is same as RA/RB/RC, right? We will have the voltage, VAB value will be equal to 0, and correspondingly the output voltage also will be equal to 0. Lux is generally the unit of the light. So generally people will call it as lumens or lux, both are same. Okay, meter, candle, lumens or lux. It is just the unit of the light which falls on the photocell. Okay, so depending upon the light falling, the resistance is going to decrease. So now at the second part, so in the first part, VAB and the V0 both will be equal to 0 because the resistor has become is remaining at 500, which will have a balanced bridge. So because of balanced bridge, VAB will be 0. V0 is equal to VAB into minus RF by R1 also will be equal to 0. Now when we have this 0.61 lux, then the resistance reduces to 6.5 kilo ohm. So del R will be effectively the value which is 500 kilo ohms minus 7.5 kilo ohms. Rather, it should be the other way around. 7.5 kilo ohms minus 500 kilo ohms will be del R. Okay, 7.5 kilo ohms minus 500 kilo ohms, that is minus 492.5 will be the value of del R. So the formula again is just the same, no difference at all as far as formula is concerned. That is same formula with a minus sign here. Okay, as I said, minus should have been there. So minus of minus 492.5 will be del R. VDC is same 10, 2 into 2 into 500 kilo ohm. The del R value is minus 492.5. Del R value is minus 492.5. So that is the value of VAB. And then the value of V0 will be just multiply the VAB by minus RF by R1. Minus RF by R1. Okay. So, that finishes the problem. So next we will go for 6.12. The circuit of the figure 6.12 uses a strain gauge. So in place of now the thermistor or the photocell, we are using the strain gauge and has the following specifications. The unstrained resistance of each of the 4 elements of the strain gauge is 120 ohm. VDC is 5 volts and the op-amp supply voltage is plus or minus 10 volts. R1 equal to 100 ohms, RF equal to 47 kilo ohms. determine the output voltage V0 if the change in the resistance of each of these strain gauge element is 0.1 ohm. Okay, so if you put, if you go back and see this figure 6.12, right? 6.12, which is the strain gauge you're trying to use there. Okay, yes. So this is the strain gauge. This is the strain gauge where all the 4 arms are there. Okay, 2 arms will behave differently and 2 arms will behave differently. That is, if you see over here, when the weight is placed on the platform, RT1 and RT3 both decrease in resistance. RT1, this is RT1 and this is RT3. Both will decrease in resistance. Then RT2 and RT4 will increase in the resistance by the same number of ohms, del R. Okay, by the same number of ohms, del R. So the formula for VAB is corresponding to this is what we need to use, minus VDC del R by R, and the value of V0 will be minus of minus will become plus, so then you need to multiply by RF by R1. So this is the formula which we need to use. Okay, this is the formula which we need to use because what we are asked there is just the value of the V0. Determine the output voltage V0. Okay, so to determine the value of V0, okay, we just need to go there and find out, substitute it here and find the value. So VDC is 10. Del R is what we need to, it is given as 1.1 kilo ohm. This is 120, I think 0.1 and 120. Is it kilo ohm or ohms? So 1.1 ohms and 120 ohms. Okay, 0.1 ohms and 120 ohms is what is the value of del R and R. RF by R1 is, again, we can find out RF is 47 kilo ohm and R1 is 100 ohms. Okay, this is 100 ohm, this is 47 kilo ohm. So try to put proper units. So 47 into 10 to the power of 3 divided by 100, and this value will be 0.1 divided by 120, then multiplied by 10. Overall, you might get a value which is something like 3.917 volts. 3.917 volts. So you can write down somewhere. The answer for this will be 3.917 volts. Okay. So thus you can find out the value of the output for 6.12. So is it clear? So now we will go for the comparator topic. For the basic comparator of figure 8.1a, Vn is equal to 2 volts peak to peak sine wave at 1 kilohertz. V reference is equal to 500 millivolts. R is equal to 100 ohms. And supply voltage is plus or minus 15 volts. So peak to peak is 2 volts, means positive from -1 till +1. From -1 till +1, peak to peak will be 2 volts. So single peak will become 2V max is equal to VPP. VPP is 2V max. V max will be equal to 1 volt. And the value of V reference is 500 millivolts, that is 0.5 volts. So this is 0.5 volts. V max is 1 volt. So if you go back, R is given and supply voltage is given, that is no meaning at all. Draw the output waveform is what we want. So we will go to the page 326 over here and see what is the what you call output corresponding to that. So if you see here, this is a problem wherein he has taken the value of this might be, I don't know, might be 4 volts or 5 volts Vmax. So that might be 8 to 10 volts peak to peak. And the clipping, the reference voltage is occurring at, the reference voltage is at 1 volt. But now we have this as 1 volt and this has -1 volts, and at 0.5 we have the reference value. Okay, reference value. So in this case, when the reference value is at 1 volt and when the peak value is somewhere around 4 volts, okay, approximately 4 volts, then corresponding to this points, you will get, between this point and this point, you will get high. Between this point and this point, you will get low. So now, if we consider this as a, 2 volts peak to peak, then at exactly the middle of this, it will be, 0.5 volts or 500 millivolts. So you have to pull that down, and only for the small portion over here, you will have the high, and for the rest of the portion, that is from here till here, it will become low. Okay, for a small portion it will be high, and for the rest of the portion it will be low. So that is only for might be approximately half the waveform in the positive cycle. Okay, approximately half, not exactly, but approximately half of this, because 0.5 is half of 1. Okay, because it's a sine wave, it's not a triangular wave. If it's a triangular wave, then it will be exactly half. If it's because it's a sine wave, it might be a little more than half, okay, of the positive portion of the waveform. It will be high. For the rest of the portion, it will be low only. Okay, it will be bigger than this. It will be bigger than this portion because we are in the middle. Then we go for the next topic, right? So output waveform we need to draw. Then repeat the problem 8.1 for V reference equal to -0.1 volt. So -0.1 volt is similar to this case. So here it is -1 volt reference voltage. So positive portion will be longer, negative portion will be smaller. Now we have peak to peak equal to the 2 volts, that is 1 volt here and -1. Out of that, -0.1 will be the very small portion during which the V reference will be there, and only for that portion you will have the positive waveform, and for the rest of the portion you will have the negative waveform. Okay, so that means when I take here -1, then for this portion, when I take 0.1 -0.1, then whatever portion comes here, for that it will be low. For the rest of the portion, it will be high. So this will be, so to say, on period will be larger than off period. Here, on period will be smaller than the off period. Here, it will be the reverse because you are having reference voltage as negative. So below the reference, it will be negative. Above the reference, it will be positive. Comparator, what it does? Below the reference, it will be negative. Above the reference, it will be positive because this is a positive or non-inverting comparator. Non-inverting comparator or positive comparator. Okay, non-inverting comparator or positive comparator. So above the reference voltage, it will be high. Below the reference voltage, it will be low. That is the point to be remembered, whether it is this or this. Only that here we have V reference positive, here we have V reference negative. So below the V reference, it will be negative. Above the V reference, it will be positive. Okay, so here positive cycle will be smaller, here negative cycle will be smaller.